back it out. All right, so this is starting on page 38 in our packet. We're looking at example 4. We have to remember our product of powers property. Remember when our bases were the same and they're being multiplied together, what did we do with the exponents, Logan? What do we do with them? Our bases are the same, they're being multiplied together, so we can do what with the exponents? Do you remember? Not divide, not subtract, we add them, we can add them. So now we have to remember our integer operations. This is why we started refreshing integer operations this year, right? Because we have to use them right away. So an expression in its simplest form, if it contains no like bases and no negative exponents. So what would we do first? Are we gonna fix our product of powers rule first? Or should we use our negative exponent first? What should we deal with first? What would you do? Exponent. You think powers or the negative exponent? What would you do, William? You would deal with our negative exponent. So I would work with product of powers because guess what our negative exponent does? It adds fractions into the mix. And then we have to multiply, and then we have to use our quotient of powers property. So we're going to start with our product of powers property. You could go through the other way, but it makes it a little bit trickier. So here's what they did. 5 to the power of 3 times 5 to the negative fifth power. These are being multiplied so we can add them. So essentially 3 minus 5 or 3 plus a negative 5. What's 3 plus negative 5?
Negative 2.
Negative 2, because our bigger number is negative. So this is 5 to the power of negative 2. So that's what I'm putting in my packet there. Now, yesterday, we learned that anything to the negative power is the multiplicative inverse. So I have to switch. I got to flip it. So now I'm going to put 5 to what power as the denominator? Is it still negative 2? No, it's the same but positive. So instead of negative 2, what's the opposite of negative 2? Positive 2. So 1 over 5 squared. So this is 1/25th, right? Because 5 squared is 2 factors of 5. 5 times 5 is 25. So simplified, 5 cubed times 5 to the negative fifth is 1/25th. It took a few steps to get there, right? So let's try this. Our bases are the same. Excuse me. They're being multiplied. Our product of powers rule says when we have the same bases or like bases, we're going to do what with the exponents, everyone? Add them. So I have 3 to the 9 plus a negative 4, or 9 minus 4, which is equal to 3 to what power? The fifth power. If we wanted to simplify further, I would suggest using your, or you could separate this into 3 to the third, which we know, and 3 squared, so 9 times 27, but still not fun. So 3 to the fifth power. Remember, we have that caret that helps us with our exponents, and that is 243. Okay. So now we have another example, except this time it's more algebraic because we've got letters involved instead of just numbers. So now looking here, we have quotient. of powers property. Do you remember our quotient of powers? Let's go back up here and remember our product of powers is to add exponents of like bases. So if our product is to add exponents of like bases, what is our quotient of powers property?
Subtract.
Subtract exponents of like bases. So we put these notes here to refresh our memory, so we don't have to turn all the way back in our packets. And down here, we can say this is to subtract exponents of like bases. Now we do have to be careful with our integer rules. So they took, it's always top minus the bottom. So we took our base and said -1 minus a -4. What do you see that we have to do before we can subtract these? What do you do, William? We're essentially going to keep, switch, right? Keep, change, opposite. So we really have -1 plus 4. When our signs are different, we subtract. 4 minus 1 is what? 3, and our bigger number was positive. So this is W cubed. You see that, how we got those things? I just remembered that anytime my speakers are turned way down, the volume doesn't record as loud. All right, so check. Our quotient rule means we're going to subtract exponents of like bases. So try that check. What are you going to do? The first part of them, yep. Okay, so we have the like base of B, and it says we subtract our exponents. It's always top exponent minus bottom exponent. So that's always good to remember too, and good notes to have for the quiz coming up. So we're gonna turn around the stuffs up here. All right, so -7, that's our first, that's our top, minus -4.
It's B to negative.
Okay, so we gotta simplify further because we can't have negative exponents. So this is B to the negative what power?
3.
-3rd power. How would I write this properly? My negative exponent has to go to the bottom. Send that negativity to the basement, I always say. We don't want any negativity here. Preferred parenting tactic. Oh no.
Like here.
We can't allow any negativity. Okay, no negativity.
How about?
All right, so we're gonna hop ahead. I want you to take some time to finish page 41. So 7 through 12 should be able to. Oh, you don't need 10 minutes, do you?
Yeah.
Like, okay, sure, 10 minutes.
Let's go. Let's go, baby.
So take some time to finish that, and we'll go over it in just a few minutes. This is page 41. Some of them are product of powers. Remember, product means we're multiplying. Some of them are quotient, and some of them are more product. Remember, your negative exponents need to go to the basement, need to be flipped.
Not nice.
No. All right, what did you guys get for number? Oh man, hold the phone. What'd you guys get for number 7?
Nine to negative two. Nine to negative seven. 1/9.
All right, guys, come back. You gotta turn your voices off now. All right, looking at number 7. We have the same base, right? So our base is 9. We can add these. What's 4 plus a negative 6? So we have 9 to the negative 2. Can I leave it like this?
No.
No, we have to send that negativity to the basement. So it becomes 1/9 to the
Second.
second power. What is 9 squared? That's one we can do.
81.
81. So we would say 1/81. Okay, so from here to here. Same with number 8. Our base is the same. So we're adding them because that's our product of a power property. Our voices are off. -9 plus 3.
Negative 6.
We can't have that negativity. All right, so we've got 1/y to the power of 6. And that's all as simplified as it gets. Okay. Now, our quotient of power property says we do what with our like base exponents? Subtract. So x, careful here, -8 minus a -12. We have to keep change, or keep switch. So we have x to what? The 4. Can we simplify that? Nope, and it's positive, so we can allow it. Same thing with number 10. -13 minus a -2. So we have to keep switch. This becomes d to what power? What's
11.
13 minus 2? Good, -11. We can't allow that negativity, so we have to switch it to the basement so it can be positive. Questions on 7 through 10? Those are just following the rules. Following those same patterns. All right. Now, we're going to figure this out. Our product of power rule says that we add them. So we have -7 plus 7 on our 8s. And we have 4 plus a -4. What's -7 plus 7?
Oh, no.
0. What is 4 plus -4?
1. 0.
Zero.
What the answer is?
Good. Anything to the power of 0 is equivalent to
1.
1. Anything to the power of 0 is equivalent to 1. 1 times 1 is 1. Did you guys get that?
Yeah.
Now you see it. Use those notes, guys. Select all of the expressions that are simplified. Is the first one simplified? Yes. Is the next one simplified?
Yeah.
No. We can't have negative exponents. But it's negative. So we can take it out of the basement. How would we simplify this? N to what power? The 5th. How would we simplify the second one? Well, first we would have n to the 6 minus 8, which is n to the -2. Can I allow any negativity? No negativity allowed. That's how we would simplify it. Is this simplified? Yes. we don't have multiple of like bases, we have different bases, we can't go any further, and is this one simplified? Yes. So these two are, okay? All right, let's look at some apply here,
What page?
back to 39, page 39. One strand of human hair is about 1/10,000 inch in diameter. The diameter of a certain wire for jewelry is 10⁻² inch. Remember, this is like 1/10 squared. That means there's 2 zeros down there. How many times larger is the diameter of the wire than a strand of hair? So this is the hair, this is the wire. Well, how could we write thousands? How could we write 1,000 as an exponent of 10? Well, how could I write 1,000 as a fraction? 1/1,000, right? So this is 1,000. So how could I write 1,000 as a factor of 10? How many zeros are there? 3. So how could I write this as a negative exponent? Can I write this as a negative exponent? Yes, 10 to what power? -3, let's say, dude. All right, so I have 10 to the -3rd. So we are going to take the bigger, which is 10 to the -2nd, divided by 10 to the -3rd. We're trying to figure out how many times more this is than that. So we're going to take bigger divided by smaller. Just like we were taking the volume of the bigger cube and dividing it by the volume of the smaller cube to see how many of the smaller cubes we could fit in. How many times larger? Do you see how these kind of parallel each other? Now we can use our quotient rule. Our bases are the same. So -2 minus a -3. Keep, change. This is 10 to what power? What's -2 plus 3? 1. What's 10 to the first power? 10. So it's 10 times larger. Okay, do you see how this parallels our other apply problems from before? Before we were looking at floors and tiles. Bigger divided by smaller. You know, it's distracting. All right, let's check our understanding of that real quick on page 40. An American green tree frog tadpole is about, tenths, hundredths, thousands, 10,000s, 100,000s.
1 million.
Kilometer. So let's write that. This is tenths, hundredths, thousands, 10,000s, 100,000s. So this is like 1/, the place value was 100,000. So I'm gonna write 100,000 here. So this is like 1/10 to the what power? Good. How many zeros are there? 5. 1, 2, 3, 4, 5. 1/10 to the 5th power. How could I write that as a negative exponent? 10 to what? 10 to the -5th. Excellent. So this is equal to 10 to the -5th power. So the largest indoor swimming pool is 10 to the -1st power kilometers wide. How many times longer is the width of the swimming pool than the length of the green tree tadpole? So how many times longer? We know what's longer, the swimming pool. So we're going to say 10 to the -1st divided by the smaller. We have big divided by small to see how many times the smaller can go into the larger. Now we write out our quotient rule. We have the same bases that are being divided. So we can subtract our exponents. Okay, we should be able to do this. Keep, change, change. We end up with -1 plus 5, which is what? 4. 10 to the 4th power. Remember, tens, we write that many zeros. So how many zeros are in my answer? 4. So I'm writing my 1 and then 1, 2, 3, 4 zeros. So 10,000 times. 10,000 times. We're not done.
Hey.
We still have 3 minutes.
Oh, it's, what are we doing?
So you've got time for at least one. Look at number 13. This apply problem directly relates, right? This is tenths, hundredths, thousandths, 10,000ths of a kilometer. So how many zeros are in this? 1, 2, 3, 4. So that's 10 to the 4th. How do I write that as a negative exponent? 10 to the -4th. All right, the diameter of a bacterium is much smaller. So how many times larger is this dish than the bacterium? We can set up that problem. Give this a go. You have 2 minutes. It should take you 1 to finish this, 1 to put your stuff away. Try it out.